So let's begin. And again, if anybody has any questions, then please stop me and ask. I mean, the goal is that this should be, clear to everybody. So here is an overview of the talk. So I'll start by explaining the problem that we were trying to solve, what's called the monomials of Boolean functions and how they look. I'll tell you about two interesting connections where this question comes up. One is in trying to solve or understand better the log-rank conjecture, which is a famous open problem in communication complexity. And the second one is connection to a different conjecture called the union-closed conjecture, which is a different famous conjecture in combinatorics. And I'll show you how these things get connected to both. And then we actually proved something. I'll tell you what we proved and some ideas about the proof. So monomials of Boolean functions. So here is going to be our main player throughout the talk. You choose an arbitrary Boolean function from n bits to 1 bit. And you write it as a polynomial. So as a polynomial, I mean over the real. So it's a real polynomial. So x to the s is just a shorthand for the product of the variables in the set s. So s is a set of variables. This is a product of the variables in the set, x to the power s. And it's a fact that any polynomial, any Boolean function can be written in exactly one way, in a unique way, as a multilinear polynomial over the real. So multilinear means that every variable appears with degree 0 or 1 in every monomial. So you never have like xi squared, because over 0, 1, any variable squared, xi squared is the same as xi. So just one way of writing it. And what we're going to care about is not so much this polynomial by itself. These coefficients are some real valid coefficients. What we're going to care about is that which coefficients are non-zero. So that's going to be the set of monomials associated with this Boolean function. So it's a set of sets S of variables such that the related or corresponding coefficient Fs is non-zero. So this monomial actually appears, in the expansion of this function. And what we're going to study is a combinatorial structure of the set system of monomials, or the family of monomials, where we completely ignore the coefficients, whether they're positive, negative, what values you get. We're going to completely ignore this information and just study the set of monomials that happen to appear in this Boolean function. And I'll tell you something about what we're trying to prove in a few minutes. But first, let me show you two examples just to clarify the definition. So here's the function. So here's one example, the end function. So the end function, outputs 1 if all the inputs are 1. Otherwise, it outputs 0. If you want to write it as a polynomial, it's just going to be the product of all the variables. Remember, variables are 0, 1. So just the product is going to be 1 if they're all 1. Otherwise, it's going to be 0. So such a function has a single monomial, right, which is a set of all variables. And that's it. It's, in some sense, the simplest possible polynomial. It's just one monomial. Okay. Now let's look on the OR function, which is going to be actually very different in this definition, in this sort of viewpoint. So the OR function is sort of the opposite. It's going to be 1 if at least one of the variables is 1, and you can verify the simple exercise. It's really this definition, because if any xi is equal to 0, then this is 1. That's fine. But if every xi is equal to 1, this thing becomes 0, then 1 minus that becomes 1. So if you expand this now into a linear combination of monomials, what you're going to find that really you're going to find here all monomials, all possible monomials, actually except for the constant term. So you get really essentially all possible monomials. So under this definition of counting the number of monomials, the end function is sort of the simplest it could be. And the OR functions is essentially the most complicated you could be. You have all monomials. Okay? And we're going to try to understand these monomials not for the ends or the OR, but for like arbitrary Boolean functions. So I think now is a good point to make sure that everybody understands the definition of what we're trying to understand. Which monomials appear in a Boolean function? Any questions so far? Now, if you think about like very common Boolean functions that we study a lot, like OR, like we've seen, or parity, or random functions, you're gonna see basically all monomials, like a very, very large number of monomials. So from our viewpoint, they're complicated. We're not going to care much about them. What we are going to care about are functions that happen to have few monomials, a small number of monomials. And what we're going to understand is, what examples are there for such functions, and can we classify all Boolean functions with few monomials? And then finally, why should we care? Like, we're going to see how this gets connected to interesting applications. So we saw one example, the end function has a single monomial, and of course you can take the end of all the variables or a subset of the variables. It's going to be single monomial. And the question is, are there other natural examples beyond the end function? And I'm going to show you one more example, or family of examples, coming from decision trees. So what is a decision tree? A decision tree is a computation of a function that you do by adaptively querying bits. So here, for example, in this diagram, I query x1, the first variable. If I happen to the 0, I go to the left. If I get 1, I go to the right. And at each part, if I went to the left, I'm going to query x2. And based on the value, I'm going to give you the results. And if I went to the right, if x1 was 1, now I decide to query x3. And based on its value, I give you the answer. Okay. So I'm going to show you in a minute that, decision trees are going to give you another natural source of functions that have a small number of monomials. So here's a claim that we're going to prove now. It's just going to be a good warm-up for us. If a function is computed by a decision tree of depth d, meaning you query d variables adaptively, then it has at most exponential in d many monomials. In particular, if d is a constant, you're only going to see constantly many monomials. And concretely with 3 to the d, with the bound that we'll prove. And the proof is going to be basically by doing induction on d. So if the depth is 0, meaning you query nothing, then the function is a constant. So you either output all 0 or all 1. So it has at most one monomial, right? Inductively, let's say you query, for example, x1 at the top. Then you go other left if you queried 0, or you go right if you queried 1. So if I want to expand this polynomial, it's going to be, if x1 is 1, now compute the function on the right. If x1 is 0, so 1 minus x1, compute the function on the left. And now fr and fl are functions computed by depth d minus 1 decision tree, because I already queried x1. So now you just extend everything and you count, right? The number of monomials here is at most the number of monomials on the right, plus twice the number of monomials on the left, so they have 1 minus x1 here. And this is like in the worst case, there's no cancellation between them. And you do the math, you get 3 to the d. So it's a very simple exercise. So we just do it by induction. So we get now another source of natural functions that are sparse, which are decision trees. Okay. So now we can ask ourselves, well, are decision trees the only example? And somehow we already know the answer. The answer is no. We saw that end is also an example of a very sparse Boolean function. So we have 2 examples so far, 2 families of examples, end of several bits and decision trees of low depth. So since we have 2 different examples and they're not, one is not containing the other because, then what you would want to do is just try to combine them together. So let's define a new model called end decision trees that tries to marry decision trees with ends of bits. So what is an end decision tree? So it's like a decision tree, except that every node, instead of querying a value of a variable, you're going to query the value of an end of some subset, arbitrary subset of variables. So for example, here, I have 3 arbitrary sets of variables, A, B, and C. Doesn't matter how big they are. This node x to the A, what it does is compute the end of all the variables in A. If the end is 1, if they're all 1, it goes to the right. And if the end is 0, if at least one of them is 0, it goes to the left. And you can see that if I write this as a polynomial, the fact that these are monomials, or A is big maybe, but not a variable, just means that these monomials have more variables in them. But it's still going to be sparse, right? Like in this case, it's the depths to n decision tree. It doesn't matter how big A, B, C are sets. It's always going to have just 4 monomials. Okay. So it shows that in this decision tree model, if the complexity that we care about is a number of monomials, then we could replace querying bits with querying ends of bits. And now this model generalizes both the end function, which is just querying a single end, and it also generalizes decision trees, which said we're allowed to query only bits, not ends of bits. So you can sort of take this claim I showed you before, and basically by the same proof, you can prove that if f is computed by a depth d and decision tree.
So I have sorry for interruption. Yeah, so for the last slide, you mentioned that, so I'm talking about the last slide. So for the last slide, you mentioned that the adaptive querying d ends of input bits. So how does this correspond to the example? So is that the cardinality of A or something like that?
No. So you don't care. So one query, single query, is allowed to specify any subset of bits.
I see.
And the result you get is the end of these bits.
I see. Okay.
So you still get just one bit as a response. But now I'm not limiting you on how many bits you're computing the end of. But you're not allowed to query these bits. You only have to query the end of these bits.
Okay. Thanks.
And this is sort of like a very weird model, but it's sort of the model that you get by trying to combine decision trees with ends, right? And I'll show you in a minute, this is actually a model that's going to come naturally in some cases. Okay, so going back here, so I'm claiming that the same claim I showed you like 2 minutes ago that said that a depth decision tree has at most 3 to the d monomials, generalizing just in an automatic way for n decision trees, because replacing variables with ends doesn't increase the sparsity, the number of monomials of a polynomial. And the proof is the same. And basically what I want to tell you about is that this is really the only source. Up to some quantitative losses, we can prove that any Boolean function that is sparse must be computed by a low depth end decision tree. So I'll tell you what the result is in a minute, and then I'll tell you how it comes up naturally in a couple of applications. So this is a technical theorem, so let's go through it together. So let f be an arbitrary Boolean function that has small m. So I'm going to use small m to denote the number of monomials of this function. Then what we're going to prove that this function can be computed by an end decision tree, by this model, whose depth is what? Well, it's not log m, which would correspond to what we saw in this decision tree example, log m to the 5. So it's polylog m. And we're also going to get this extra log n term here that probably shouldn't be here, but we can get rid of it. So again, so commenting on the parameters, if this was log m, this would exactly match our example. But for technical reasons, we get log m to the power 5. So it's polylogarithmic, it's self-logarithmic. And even more annoying, the number of variables should not really be important here, but somehow it comes up in the proof. And we don't know how to get rid of it. And really what I conjecture is the right bound should be order log m, because that would actually match the example of n decision trees. If order log m would be the right answer, then this would give like a match in upper and lower bounds up to constants. And this would also help us improve some of the applications that I'll get to in a minute. Okay, but this is the main result. Are there any questions about any of the definitions here, or what the result is? So again, if you know, yes, go ahead. Yeah.
Yeah. So this theorem is saying something about the decision tree. So if we instead use our decision tree or something like this, so I guess the result will be the same.
No, because in this basis of monomials, also are very complicated. They have maximally many monomials. And ends are simple. If you want to work with Ors, you want to allow monomials where instead of multiplying variables, you're multiplying one minus a variable.
I see. Okay, thanks.
Sure. Okay. I'm going to tell you about some interesting extensions of this question, not of the result, towards the end, and in particular, there's a very natural extension related to Fourier sparse Boolean function that is still open and also has a very interesting connection to applications. So I'll get to that towards the end. So this is just for this 0-1 basis, and that's just for counting monomials in the standard monomial basis. Okay, but then if there's too many parameters here, then the way to think about it, that essentially n decision trees are the only way that you can get sparse Boolean functions. Okay, so now I want to tell you about how do we prove this. So this result about n decision trees really follows from a much more combinatorial result, which is really the main thing we prove, which is the set systems of monomials of Boolean functions are not arbitrary set systems, they have structure. And the structure concretely says that they have small hidden sets. So I'll define hidden sets in a minute, but basically it says that there is a small set of variables that intersects all the monomials. So they're not arbitrary looking. So let's define this formally. So if F is a set system, a family of sets, we say that the set H is a hidden set for F if it intersects all the sets S in F, except, of course, the empty set. So meaning that the set of H is the variables that every set in the set system contains at least one of the variables in H. Okay, that's what's called the hidden set. And really our main technical result, from which the result of a decision tree follows relatively simply, is that if I give you any Boolean function with m monomials, the set of monomials has a small number of variables, polylog m, log m to the 5, such that these variables intersect all the monomials. So the monomials are not random looking, they're sort of concentrated on a small set of variables. At least, one of the variables is concentrated in a small set. Okay, that's a hidden set. Okay, so now I want to tell you about two applications where this question comes up, and the first one was our original motivation was trying to understand the log rank conjecture. Actually, before doing that, are there any questions here going back to the definition of what a hidden set is? No. Okay, so it's one. Okay. So log rank conjecture. So the log rank conjecture is a very famous fundamental open problems in the area of communication complexity, and actually, it's a mathematical problem, and the same mathematical problem I'll define in the next couple of slides actually came up independently in several other areas of mathematics, such as graph theory and geometry. But I'll still describe it from the viewpoint of communication complexity because it's more natural, I think, for us as people studying, CS theory. And really, it is a question about the structure of low-rank Boolean matrices. Yes.
I have a question. So, in the last slide, so for the hidden set, you are only going to show the existence. Is there any explicit construction for this hidden set?
That's a good question. First of all, it depends on the function, right? So every function is going to have a different hidden set. So it's not universal in any way, right? So it depends. But if you give me a function and you describe its monomials, then really what we do actually allows you to find it. But that somehow but finding it somehow the less interesting part. The more interesting part for the application is just showing it exists.
Okay. So in general, if we are not focusing on a specific Boolean function, but is there any hidden set for all Boolean functions with this size m being small m?
No, because think about the Boolean function as just a single variable, like xi, right? So you need to have xi in your set. So it's not universal. So it depends on the Boolean function.
Yeah, I see. Thanks.
Okay, thank you. Thanks for the question. Okay, again, to this log rank conjecture. And like I said, log rank conjecture is really a mathematical question about the structure of low-rank Boolean matrices. So what's the question? Here's a question. So let A be an n by n Boolean matrix, a matrix with 0, 1 values, and we're going to compute its rank over the reals. And let's use R to denote its rank. And what we're going to care about is a regime where the rank is really low. So a random matrix going to have rank close to n. Here we think of the rank as being much less than n, maybe log n or polylog n, like really below n. And the question we're going to ask ourselves is, what is the structure of such low-rank Boolean matrices? How can we construct them? So here's one way to construct them. So you take your matrix and decompose your matrix into rectangles or submatrices. When I say rectangle, it's the same as the submatrix, just different terminology. Like here, for example, I decompose into like 7 of them. And in each one, you just put a value, like 0 or 1. So my claim is if you decompose your matrix into R submatrices, and you color each one either all 0 or all 1, the rank of your matrix is at most R, because you could write your matrix as the sum of these submatrices, and each submatrix is either the all 0, so it has rank 0, or it's a rank 1 matrix, because it's a rectangle with all 1s in it, and rank is subadditive. And the log rank conjecture really speculated up to some quantitative losses. This is really the only thing you can do. Meaning that if I give you a low rank Boolean matrix, the only way to generate them is to find an efficient way of partitioning your matrix into submatrices, a small number of them, that are monochromatic, meaning every submatrix is either all 0 or all 1. Okay, so more quantitatively, here's a conjecture. So let A be a Boolean matrix whose rank is R, and again, rank is always over the reals. Then you can decompose your matrix into a small number, capital R, which happens to be the conjecture at most what's called quasi-polynomial in R. So it's exponential in polylog R, polylog small r, monochromatic rectangles for some constancy. That's a conjecture. How come people go to this conjecture? Why this weird bound of exponential of log C to the R? Well, the original conjectures people had actually in graph theory coming from the 70s were much stronger. Well, what if capital R equals small r? Or maybe that people found counterexamples. Maybe capital R is linear in R, maybe 100 R. No, that's also not true. What about polynomial? Also, people have found counterexamples. So the best examples we know of matrices are matrices where what you need for the number of submatrices is to be rank to the log rank, meaning that in this expression C is 2. So we know that there are examples where you need C to be at least 2 in this conjecture. And by the conjecture that C, if you choose C to be a large enough constant, at least 2, that this should hold for all Boolean matrices. Okay, so the reason people go to this weird conjecture is because initially they had strong conjectures that turned out to be false, because people found like better and better examples for such low-rank Boolean matrices. So this is our conjecture. So turns out you can prove a very simple bound where you lose something exponentially. Where you can, to prove it's an exercise that you can always choose capital R to be exponential in the rank. And one thing I proved a few years ago is that you can be exponential in the roots rank. And that's the best we know so far. And this is still very, very far from exponential in polylog rank, right? This is exponential in root rank, this is exponential in log rank or polylog rank, still exponentially far off. And so people don't know what to do, so they say, well, let's look on some special cases. So I'll tell you about one special case that people care about a lot, which is what's called lifted functions. But before doing that, to be convenient to view our matrices, instead of matrices, to view them as two-party functions, which is the usual way we view, problems in communication complexity. So we have two players, X and Y, let's call them. So we get an input, X gets an input and Y gets an input, and they want to figure out what the output is, which is 0 or 1. So you can use it as a matrix, where X is the rows and Y are the columns, or you can do this as a function from X times Y to 0, 1. There are two equivalent viewpoints. And for us, for the next couple of minutes, it will be convenient to view this as the function case, because it's going to be a natural way of coming up with a family of interesting examples. So these examples are called lifted functions. So a lifted function is a matrix or a two-party function that you build in the following way. It has two components. It has an outer function, which is just a Boolean function on n bits. And there is a gadget, which is a function that takes two inputs, X and Y, and outputs the value 0, 1. And the lifted function is it's a function, it's a larger function. So one player gets n copies of x inputs, like x1 up to xn. The other player gets y1 up to yn. And what they do to compute the matrix or the two-party function is the following. They apply the gadget on x1, y1, x2, y2, x3, y3, up to xn, yn. They get n bits, and then they apply the Boolean function on these n bits. So you can fit in this diagram that gives this n copies of the gadget on x1, y1, x2, y2, and so on, and then we feed the output to f. Anyway, it's a way of generating interesting examples in communication complexity, and there are many natural functions that we study in communication complexity happen to look like that, with maybe sometimes a complicated outer function, but a simple gadget. So I'll show you one example, which is what's called end functions. End functions correspond to the gadget just being the end of 2 bits. Or if you use 0, 1, it's the product of the 2 bits. So what is an end function? So again, I start with an arbitrary Boolean function on n bits. And I build a two-party function. So the first player gets x1 up to xn. The second player gets y1 up to yn. We end their inputs, we get a joint, n-bit value, and we apply the Boolean function. So that's a way of generating matrices from a Boolean function and ends. And why is this interesting for us? Because it turns out you can prove that the rank of this matrix corresponding to this end function is exactly the number of monomials of this Boolean function. So really, if you want to solve the log rank conjecture, even in this very special case of end functions, what we really need to understand is the structure of these monomials of Boolean functions, which is how we got to studying this question. That was our motivation. So what can we prove? So we can almost prove the log rank conjecture for this very special case of end functions. So again, let me remind you of the setup. So you start with an arbitrary Boolean function on n bits. You build a matrix we call capital F. So its row x is values in 0, 1 to the n. Its columns y are in 0, 1 to the n, and the xy entry compute as follows. You take x and y, you get an n-bit value, and you apply the Boolean function small f on it. So it's a 2 to the n by 2 to the n matrix. And what we can prove is the following thing. Assume the rank of this matrix is R, which is our assumption for the log rank conjecture. We want to prove it can be decomposed to a quasi-polynomial number of monochromatic matrices. And we can almost prove that. See, this is this polylog R here, but we get this annoying log n term that we couldn't get rid of, coming from our decision tree model. So in particular, if you could get rid of this log n term in the decision tree model, as one of its corollaries, it will complete the proof of the log rank conjecture for this special case of end functions. And so far we're almost there, but not quite there. So after this log n term, this will prove our conjecture. And you see here, see that we get this 5, which is a constant that's more than 2. Okay. And maybe this 5 can be improved, but we don't know how to do it. Okay, so this was one motivation. I want to tell you now, so next about a different motivation for this question. But first I want to hear, are there any questions about the log rank conjecture or this specific case or anything that I said about it? Okay.
I have a question.
Yes,
so,
go ahead.
For the claim in your last slide, so it seems that if we use and as a gadget, then if we use and as a gadget, then we can get something. Let's see how to say. So how about can we use any other function as a gadget, and will they give the similar result?
Okay, so you can use other gadgets, but other gadgets would lead into other structural problems. So if you use, for example, XOR, you get the question about what's called XOR functions. I'll talk about later toward the end of the talk. If you use OR, it's going to be the same question. You need to change the basis of just negating all the variables. The same thing. If you use a complicated gadget, then we know that this is actually related to what's called the query complexity of F in the decision tree model. which we understand completely. So for complicated gadgets, we understand this problem, but it becomes more complicated for simpler gadgets because there somehow the internal structure of F plays a more important part.
Okay, I see. Okay, I see. Thanks.
And then all of these are just very special cases of the logarithmic conjecture. But again, the main reason to study these special cases is to build, more tools, more intuition that hopefully might help us in proving, the full conjecture. Because even for these special cases, we saw in many cases we're stuck. And then, again, I'll talk about this sole case towards the end of the talk. I think it's a very interesting question. Okay, so let me tell you now about a different motivation, which is connection, something called the union closed conjecture, which is the conjecture in combinatorics. So let me tell you what this conjecture is. It's very simple to state, but very hard to prove anything about it. Let F be a set system, family of sets. We say it is union closed. It's a definition. If it satisfies the following property, takes any two sets, S and T, in your set system, then the union is also in your set system. Okay, that's a definition of a union closed set system. It's closed under unions. And here's a conjecture of Frankel from the 80s. It said, let F be a union closed set system, then there should be an element in your base universe that belongs to at least half the sets. Okay, so like one example, let's say your elements are 1, 2, 3 up to n. Your set system are all the sets. Then every element belongs to exactly half the sets. And what Frankel conjectured is that basically that's going to be the case always. So always going to be some element belonging to half the sets. And that's been open for like 40 years now, and nobody has any clue how to prove anything about it. So again, very easy to state, very hard to make any progress on, which makes, of course, a very fun problem to spend time thinking about. And I want to tell you why this question is connected to what I told you about the monomial structure of Boolean functions, because it doesn't seem to be related. So let me first tell you what people do know how to prove. And I'll tell you a claim that is embarrassingly basically the only general thing we know how to prove for this union closed conjecture. And the proof is going to be simple enough that it's going to fit at the bottom half of the slide. So here's the claim. Let F be a union closed set system of some M, be the number of sets. Then it has a Hittin set, a family of sets intersecting all of the sets in it of size at most log M, or really log M plus 1, but about log M. So how can we prove this? By the way, before I prove it, here's the corollary. If I have log M or log M plus 1 elements that intersect all the sets, then there has to be some element that belongs to 1 over this number, 1 over log M, fraction of the sets. And this is the best result known in general. I mean, there are some things known in special cases, but in general, that's all that we know. And the proof of this claim is really like a 3-line proof. And it's really sort of embarrassing that we can't prove anything that's much stronger. So here's the proof of the claim. So let H be a minimal Hittin set for F. So the smallest size of Hittin set for F. So my claim is that because it's minimal, for every element X in H, in the Hittin set, there must be some set Sx in your set system that intersects your Hittin set in exactly this element, and nothing else. Otherwise, this set Hittin set will be minimal. This is set Sx. And because F is union closed, the unions of Sx, all these sets, are also in F. So if I look on all the sets in F and look on their intersection with H, this contains all the singletons, all the single elements, and it's closed under unions. It contains all the sets in H, maybe except for the empty sets. So it has at least 2 to the power of H minus 1 sets, and that's at least most of the sets in F. That's it. That's the proof. So on Hittin set, that's the best part you could prove in general, because you could think about maybe your set system with all the sets, so all the sets except the empty sets. On this corollary is really what you would try to prove, that the Frankel's conjecture that really the right answer should be a constant here. And actually, the only work that I'm aware of that people were able to put this 1 to a slightly larger constant with a lot of hard work. But that's all that we know. So this is really wide open. So now let me tell you how this gets connected to Boolean functions. So take a Boolean function now, again, as we did before, write as a polynomial, and let M be the set of its monomials. Now here's an observation. Well, because f is a Boolean, we have that f squared equals f, right? F squared, you take every f of x and you square it, but because the output is 0, 1, 0 squared is 0, 1 squared is 1, f squared is f as a Boolean function. Well, what is f squared? F squared, if you expand it, what you get is exactly that. You sum over all pairs, s and t of coefficients, fs of t, and the monomial you get with xs times xt is just corresponding to the union. So you see, we get this polynomial related to the unions of sets, and it's the same as f, which is just the expansion of f. What can we deduce from that? Well, not much. But if we happen to be super lucky and there were no cancellations, because think about here, every monomial here, xs union t, on the left-hand side, could appear many, many times with many, many ways of writing a set as a union of two sets. So it has many, many coefficients hitting the same monomial, and they might cancel. But if somehow magically there were no cancellations, then what would we get? We would get that the monomials of a Boolean function are union closed. Now, of course, they're not, and it's easy to build counterexamples. But really, you can think about what we proved is that showing that even though it's not union closed, it shares some features, some similarity with union closed set systems. For concretely, both of them have small hidden sets. So for union closed, it's going to be log the set of the set. And for general Boolean functions, it's going to be polylog the set of the set. So now, seeing that it's sort of natural to think, well, can we think about union closed set systems as a special case of Boolean functions? And the answer is yes. So here's a claim. If I give me any union closed set system, I can always find non-zero coefficients for the elements in this set system, such that if I write a corresponding polynomial, it's going to compute a Boolean function. So we can really view union closed set systems as corresponding to special cases of Boolean functions. Okay. And now I think it's a very intriguing question, which is, well, first of all, an observation. These are functions where there are no cancellations when you compute f squared. And an intriguing question is, well, what is the structure of such functions? Can we say something more about the structure? And can this direction help us somehow shed light on the union closed conjecture? So I'm going to leave them both as open problems. Any questions about the union closed conjecture?
So just want to be clarified. When you say non-zero coefficients, you mean all of them are non-zero, not just some of them are non-zero.
I mean, for every set in your set system, it corresponds to a monomial, and this monomial, I'm going to choose some non-zero coefficient for it. But the non-zero coefficients are exactly the set system F that's union closed.
Any idea what kind of polynomial it is? Is it a meaningful polynomial?
Yeah, well, the way to prove it is by induction, going from low weight to high weight, but I don't know how to prove anything more interesting about it. Like, I know how to construct it, but I don't know how to prove anything interesting about the Boolean function to compute. Like maybe it's monotone, close to monotone, and other interesting properties. I don't know.
Okay, gotcha. Thank you.
I think that's sort of wide open. So I'll tell you very briefly. I mean, I'm going to slightly speed through the proof ideas because I really want to. Actually, how much time do I have left? I mean,
we can have roughly at most 15 minutes.
No, 15 minutes is fine. I'm just wondering, should I leave time for questions? I think I'm going to we can speak like 5 minutes about the proof and then briefly about the speak maybe another 5 minutes about open problems. Then we have maybe 5 to 10 minutes of questions. Sounds
Sure.
okay?
Sure.
So the proof idea is, again, what we're trying to prove here is that if I give you a Boolean function, look at its monomials, I want to show it has a small hidden set. And there is a way to write this by something called certificates. So what is certificate? Certificate is a very classical notion that people study in Boolean function analysis. And a certificate says that if you're given an input, it's enough to know a few of the values of this input and it determines the value of the function. And really a question about the heating set is really about the certificate for the all zero inputs. Because think about it, if I have a heating set for a monomial or polynomial, I have a few variables that intersect on the monomials. If I set them all to zero, I set all the non-constant monomials to zero, I get a constant function. So really the question about the heating set is equivalent to the question of proving that you have a small heating set, so a small certificate for the all zero inputs. And there is this another very well studied notion called block sensitivity that I'm going to slightly speed through, that is basically an obstacle. Block sensitivity says that you have many blocks that are disjoint, but somehow flipping them flips the value of the function, and it's well known that if you're hoping that block sensitivity at any input is a lower bound for the certificate, so the way, and we want to show that certificate at zero is small, so we do it in several steps. So first we prove that the block sensitivity of this polynomial is small at zero, using sort of classical tools from Boolean function analysis. So we're going to sort of skip through that. And there is this general connection known in Boolean function analysis that says that, well, if I define the block sensitivity of a function to be the maximal of all inputs of this block sensitivity, and the certificate to be the maximum of all inputs of certificate, then these two things are connected up to constants, up to polynomial value constants. And here what we care is not about the maximum, but about the value at zero. But it turns out that you can build examples showing that there are, like even the end function, its block sensitivity and sensitivity at the all zero input is really low, but at the all one input is very big. So really in our case, we can't really look on all inputs. We have to look on some way of giving preference to zeros versus ones. So there's some asymmetry here. So again, skipping through details, we define some asymmetric versions of certificates and block sensitivity. And really what we would like to prove is the following thing. We want to show that just because the function is past this zero version of block sensitivity is small, which you can prove in classical techniques, and then we would like to prove something similar to this and secondly, that show that, well, if this is small on all inputs and this one is small on all inputs, this we don't know how to prove, but we can prove under some additional assumption that the function is sparse, which we happen to have. So again, I'm really speaking through it because there are many, many technical details here that I don't really have the time to cover. But I just want to maybe highlight something about this overall structure of the proof here. It has three parts. One part, the first part, is bounding this sort of asymmetric version of block sensitivity. The second part is looking at something called fractional relaxations and proving some bounds on their integrality gaps. And the third part is using some type of rounding techniques. And the first and the third part here use sort of well-known, well-studied techniques. The second part is sort of new. We had to invent new techniques to prove the second part. But again, that's all I want to say because really, talking about the technical part is another full hour. So I'm not going to do that. And if people are interested, I can talk more about in the open problems session. What I really want to spend like the last maybe 5 minutes about is telling you about open problems. So really, this is a summary of what we proved. That's for an arbitrary Boolean function, its monomials are structured. And very concretely, the set system of the monomials always has a very small hidden set of size polylogarithmic in the number of monomials. And here are three open problems. So this is a bound that we proved. So we have n variables, we have m monomials. The hidden set size that we proved, the decision tree depth that we proved is that this polylog m coming from this hidden set size. And somehow when you go from hidden sets and decision trees, the way we know how to do it, you use another log n. And I think that to me the most interesting open problem here, maybe it's not very hard, but we don't know how to do it, is to have a more efficient way of moving from hidden sets to n decision trees that doesn't lose this log n factor. I don't know how to do that. That would be nice because if you can prove that, this will at least settle the Lagrange conjecture in this one case that we know how to prove something about it. Very close to the conjecture bound. And again, for the hidden set size, this 5 should probably not be here, it should be a 1, but the techniques we have, we lose the 5. Anyways, That's one question. The other ones are about trying to extend this to other settings. So here's, I think, the most interesting setting where you can ask this question, and it's maybe the next obvious step, which is moving from the end function basis to what's called the Fourier basis. So I'm sure you all know that we can write any Boolean function in its Fourier basis. So now the basis is not ends of variables, but it's really this. It's -1 to the power of some variables, if the variables are 0, 1, or equivalently, it could be the monomial basis, but then we think of the inputs not as 0, 1, but as -1, 1. If we do monomials in the basis of -1, 1, that's exactly the same as the Fourier expansion. So you see the basis of the inputs is important for the question. But for example, in this basis, parity is simple, but end is complicated. And here will be the conjecture. So take a Boolean function, and the common term here for monomials is what's called the spectrum. So the spectrum of f is the set of all its non-zero Fourier coefficients. And notice that here, unlike the case of end functions, there is some degree of freedom. I could apply any change of basis to my input space, and it's not going to change the sparsity or the number of non-zero monomials. So whatever question or conjecture we might have should be invariant to this change of basis. And really here is the natural conjecture in this basis. It said, if you have a Boolean function of spectrum of size r with r Fourier coefficients, then there is some change of basis, L, that you've applied to this function, and you look on the monomials, now they have a small hidden set. So it's exactly the same thing that we proved in the end case, except here we need to allow you to also change basis because the spectrum is invariant to the change of basis. And again, this is wide open. We don't know how to prove it. If you could prove it, this would prove the logarithm conjecture for another, even more well-studied special case called XOR functions. It would be a very interesting case to prove it in. And my third question, just a reminder about this union clause conjecture, that we know now that we can relate a union clause set system to Boolean functions f, that f squared has no cancellations. You get the same monomials as nf. And really what I think is a very intriguing question is trying to understand the structure of such functions, and then seeing if we can apply tools from Boolean function analysis to make some progress on the unit clause conjecture. So I'm going to end here, and thank you.